Hi, I'm Bob. We have solved the first 12 problems for Chapter 3. Today, let's find the answers for the remaining problems. Here's problem 13. Consider the simple regression model y equals beta 0 plus beta 1 times x plus mu under the first four Gauss-Markov assumptions. Define a variable z equals a function of x. Show that the following estimator is linear and unbiased. To show the estimator is linear, we need to show we can write it as a linear function of the outcome variable y. Let me first show you why the OLS slope estimator from the simple regression model is linear. We can write beta 1 hat as a weighted sum of yi. The weight is a function of xi. So beta 1 hat is linear. Now look at this question. We can also express the estimator beta 1 tilde as a weighted sum of the outcome variable yi. The weight is a function of xi and zi. So the beta 1 tilde is linear. To prove that the estimator is unbiased, we need to show that the expected value of the estimator equals the population model parameter. We use the method we are familiar with, that is, to replace yi with its relationship with xi and μi. Then we simplify the numerator and write the beta 1 tilde in two terms, beta 1 plus a second term containing the error term. Under the zero conditional mean assumption, the expected value of the second term is 0. Thus, the expected value of the estimator beta 1 tilde equals the population parameter beta 1. In other words, the estimator is unbiased. For the second question, we need to show the following variance of the estimator under the homoscedasticity assumption. We replace yi with the population model. We know that the variance of a constant is 0, and we can treat x and z as non-random, so the variance of the first two terms is 0. For the last term, we take the denominator out of the variance. The denominator is a constant term, and we square it when taking it out of the variance sign. Under the homoscedasticity assumption, the variance of the error term is sigma squared, so that we can reach the answer. The third question is to show that the variance of the OLS estimator beta 1 hat is smaller than or equal to the variance of beta 1 tilde. With the Cauchy-Schwarz inequality, it is straightforward to show the result. Let's do problem 14. Suppose you have a sample of size n on three variables y, x1, and x2, and you are primarily interested in the effect of x1 on y. Let beta 1 tilde be the coefficient on x1 from the simple regression, and beta 1 hat the coefficient on x1 from the regression y on x1 and x2. The standard errors of the two estimators are as follows. The sigma tilde is the standard error of the regression from the simple regression, and the sigma hat is the standard error of the regression from the multiple regression. VIF is the variance inflation factor. The R squared comes from the regression of x1 on x2. Explain why the standard error of beta 1 hat from the multiple regression could be smaller or larger than the standard error of beta 1 tilde from the simple regression. To compare the standard errors of the estimators, we first write down the formulas. Comparing the two formulas, we find that the total sum of squares of x1 in the two formulas would be the same because it is the sample variation in x1. We should consider the R squared and the standard errors of the error term sigma hat and sigma tilde. There are four cases or four situations that affect them. In the first case, x1 and x2 are highly correlated, and therefore the R squared 1 from the regression x1 on x2 is close to 1. It means the square root of 1 minus the R squared is close to 0. In the second case, x1 and x2 are almost uncorrelated. Then R squared 1 is close to 0, and the square root term is close to 1. In the third case, x2 has a large partial effect on y. That suggests that the squared sum of residuals from the multiple regression is much smaller than the squared sum of residuals from the simple regression. As a result, the sigma squared hat is much smaller than the sigma squared tilde, and therefore the standard error of the error term from the multiple regression, sigma hat, is much smaller than the standard error of the error term from the simple regression, sigma tilde. In the fourth case, x2 has little partial effect on y. In this case, the sigma hat and the sigma tilde would be similar. I summarize the four cases in the table. We find that the standard error of beta 1 hat depends on the relationship between x1 and x2 and the relationship between y and x2. Suppose x2 is almost uncorrelated with x1 and has a large partial effect on y. Then the standard error of beta 1 hat from the multiple regression is smaller than the standard error of beta 1 tilde from the simple regression. If x2 is highly correlated with x1 and has a small partial effect on y, then the standard error of beta 1 hat is larger than the standard error of beta 1 tilde. Let's go to problem 15. It is also a problem that compares multiple regression to simple regression. For the first question, the degrees of freedom are 351 in the simple regression because the number of observations is 353 and the number of estimated parameters is 2. The degrees of freedom are 350 in the multiple regression model because there is one more estimated parameter. The standard error of the regression SER in the multiple regression sigma hat is 0.753. It is smaller than the SER in the simple regression sigma tilde, which is 0.964. The reason is that the sum of squares of residuals, SSR, is smaller in the multiple regression than in the simple regression. It is 198 versus 326. From the formula for the standard error of the regression SER, we know that it mainly depends on the sum of squares of residuals. The difference in the degrees of freedom is negligible when the sample size is large. If the sum of squares of residuals in the multiple regression is smaller than that from the simple regression, then the sigma hat could be smaller than the sigma tilde. In this problem, we see that the sum of squares of residuals in the multiple regression is 198 and that in the simple regression is 326, which is much larger. That is why the standard error of the error term sigma hat from the multiple regression is smaller than that from the simple regression. For the second question, the correlation coefficient makes sense. A player becomes more experienced with more years in the major leagues. A more experienced player is more likely to have more runs batted in per year. The years in the major leagues are positively correlated with the runs batted in each year. The variance inflation factor, BIF, for the estimated coefficient on years equals 1 over 1 minus r squared 1. The r squared 1 comes from the regression of years on runs batted in per year. The problem does not provide information about this regression. We can run the regression by ourselves. You can download all the datasets from the link below. We regress yes on RBISYR. The command eReturnList shows the stored statistics after the regression. The R squared is stored in a scalar ER2. Then we can compute the variance inflation factor. It is 1.31. It's not large, much smaller than 10. The variance inflation factor measures the degree of collinearity. There's little collinearity between years in the major leagues and runs batted in per year. For the third question, the standard error for the coefficient on years depends on the variance inflation factor and the standard error of the error term. We have already had the values for the sigma hat, the sigma tilde, and the variance inflation factor. The sample variation in years is the same. So the standard error of beta 1 hat is smaller than that of beta 1 tilde. Actually, we can compute the standard errors for the estimates. For the multiple regression, we have computed the standard error of the regression SER, sigma hat. It is called the root mean squared error in Stata. We have also computed the variance inflation factor, VIF, for the variable years. We now compute the total sum of squares of x1, which is the sample variation in the variable years. Finally, we can compute the standard error for the coefficient on the variable years. It is exactly the same as the Stata reports in the result window. We can also calculate the standard error for the coefficient in simple regression in the same way. Let's solve problem number 16. It is about the r squared. We write down the formula for the r squared. Usually, the explained sum of squares increases as we add more explanatory variables to the model. As a result, the r squared is higher in the model with more explanatory variables than in the model with fewer explanatory variables. However, if the sample size changes, the r squared could become lower as more explanatory variables are added. Let's go to problem 17. Suppose that getting one more year of education necessarily reduces workforce experience by 1 year. One more year of schooling results in one fewer year of work experience. So getting one more year of schooling increases workers' wages by 0.094 minus 0.026, which is 0.068 or 6.8%. A more precise percentage is 7.0%. Notice that if there is perfect collinearity between schooling and work experience, we should drop one of the explanatory variables from the model. If there is no perfect collinearity, both variables can be included in the model. But the multicollinearity could lead to a large standard error of the estimate. Finally, I would like to show you the OLS regression result window and explain the values in the result table. In the upper left, we see the sum of squares. The three values are the total sum of squares, the explained sum of squares, and the sum of squared residuals. Then we see the degrees of freedom. Next, we find the sum of squared residuals divided by the degrees of freedom. In the upper right corner, we find the number of observations, the r squared, and the root mean squared error. The root mean squared error is the sigma hat. It is called the standard error of the regression SER in the textbook. It is an estimator of the standard deviation of the error term. At the lower part of the window, we see the estimated coefficients and their standard errors. along with the t-statistics, the p-values, and the confidence intervals. Thank you very much for completing the problems with me. See you in the computer exercises soon. Thank you for watching this video and subscribing to my YouTube channel. See you next time.